So this is what I'm calling video review, and this is to get us started with Unit 3. And so in this video, I'm going to discuss three things. Intermolecular forces, quite a bit, properties of liquids and solids, and then a little bit of phase changes. Then in our next class, we'll pick right up with these phase changes and keep moving forward in Unit 3. Now, you've likely already been reading about these things. These are going to be, as I start these topics this evening, these are going to be the things that you would read about in chapters 8 and 10 of the Adam's First Book online. All right, so let's take a look at these states of matter. Really a very simple review for you. So look at the state on the left. What would you say that it is? If you said, right, because you do already know these. If you said that on the left we've got a solid, you're exactly right. In the middle, a liquid. And then on the far right, gases. And taking a look at that gas, you can see that it's a diatomic gas, one of those diatomic 7. And so what kinds of materials are solids or liquids at room temperature? So just think of a couple of things that would be a solid at room temperature or a liquid at room temperature. And so for solid, maybe you thought wood, rock. Liquid at room temperature, maybe you thought of water. Well, and the thing is that if we change the temperature and the pressure of any material, water, wood, or rock, we can turn any material into a liquid or a gas or a solid. And there's a balance between temperature and something we call intermolecular forces that changes our states of matter from solids to liquids to gases. So let's start with these intermolecular forces. These are attraction between different molecules. Just like Route 113 is an interstate highway. It goes between two different states and it's still 113. When you cross over into Maryland, south of us, it would still be Route 113. There are 3 of these intermolecular forces that you need to know about. London dispersion forces. These are just temporary forces, sometimes just called dispersion forces, dipole-dipole, and hydrogen bonding. The whole basis for these intermolecular forces, forces that hold molecules together, is opposite forces attract. And so in our last unit, we were studying those polar molecules, and you'll remember that those polar molecules have opposite charges on opposite ends of the molecule, like, for example, water, pictured here, and those opposite ends of the water molecules attract each other. Those are intermolecular forces. Now, don't confuse these with the intramolecular forces. Within that water molecule, or within those water molecules, those solid black lines, those are the intramolecular forces. Just like if you were to play intracollegiate athletics, you would be playing for Deltec with other teams against each other, all within Deltec. And so here's just another example for you. What force is represented with the dashed black line? Hopefully you said intermolecular forces. And then with the solid black line, those are our intramolecular forces. Sometimes these intermolecular forces are also called van der Waals forces. And just so you know, because water is a very polar molecule, they do stick together. And that force that causes them to stick together to form droplets is called cohesion. All right. So if we had this ionic compound, Na and Cl, and you can see here I've put the nonmetal first, what force is going to hold these together? Well, if you're thinking, well, they're two different ions, so that would have to be an ionic bond or ion-ion forces, you're exactly correct. Now, we can always take one of these ions and use them later on, and we're going to see that as well. All right. So here's our first intermolecular force. This is called a London force or a dispersion force. These are just temporary forces. They're very weak. And essentially, these forces exist between all molecules. These are the forces that would hold elements together. These are the forces that would hold nonpolar substances together. The larger the material or molecule, the stronger the force. So for example, if we had helium, of course it would be a gas. It's not going to stick together very well, but there is going to be a little bit of attraction between those helium atoms. That would be a London dispersion force. Now, obviously, if you look at your periodic table, you know helium is a very small molecule, or small atom, excuse me. And because of that, it would have a very, very weak force. If we picked a bigger atom, like say, let's also pick another noble gas like krypton, for example, it would have, because it's a larger molecule, it would have stronger force of attraction between those atoms. All right. So if you were to be writing chlorine in a chemical equation, what would the formula be? Hopefully you're thinking, well, that's going to have to be Cl2 because it's one of our diatomics. And you're exactly right. And so it would look like this. It would be linear in shape. Now, if we had multiple of these chlorine molecules, would they stick together? Well, the first thing, exactly what we've been doing, is we've got to look to see, is this a polar molecule or a nonpolar molecule? The whole molecule, not just the bond. Well, if you were thinking nonpolar, you're exactly right, because the electronegativities are exactly the same. Because they're two chlorine atoms, right? So this is a nonpolar molecule. So here's another way to take a look at this molecule as nonpolar. So is there going, and it doesn't matter however you want to look at it, is there going to be any force of attraction between these two diatomic molecules? Well, probably not a lot because they're nonpolar. And remember, the basis for these intermolecular attractions is that opposite charges attract, and positive and negatives attract. But what could happen is there could be an electron come by or something happen. The diatomic molecule on the left, for some reason, gets polarized for just a moment, just temporarily, because the electrons, remember, are always moving. And so what happens then, if that diatomic molecule on the right should get polarized, all the electrons in the molecule on the left are going to move towards the right because they're attracted to that positive side. And so for a few moments, we're going to have this charge separation in these molecules. And so there is going to be a little bit of an attraction there, and we call that a London dispersion force. Now, what you need to know about this type of force, it occurs in your nonpolar molecules, and the larger the molecule or the atom, the greater the attraction. So again, if you're looking at your periodic table, you can see chlorine, of course, is a group 7 halogen. It's a fairly small diatomic molecule. Something like iodine would be much larger. And so the force of attraction there would be larger because there's more opportunity for the electrons to separate. All right. And so we also call this, not only do we call it a London dispersion force, sometimes we call it an induced dipole moment because we've caused this charge separation in this nonpolar molecule. The second force you need to know, intermolecular force, is called a dipole-dipole force. All right. Now don't get all worried about this word dipole. as we've been drawing the lines where the electrons are pulled in your polar molecules, those are sometimes called dipole because you've got two poles in that molecule, a negative end and a positive end. And so this is the type of force that holds all all polar substances together. And so if we had a polar material like HCl, obviously HCl is polar. The electronegativity of H is 2.1. Cl is 3.44, so very polar there. The molecules would actually line up so that the negative end of the chlorine is attracted to the hydrogen end of the opposite molecule. And this is an intermolecular force. Now, of course, London dispersion forces are going to be present here as well. But the strongest force is going to be the dipole-dipole force. And so that's something you just have to be cautious of. If I ask you to list all the forces, London forces are always present. All right, so what would you say the formula for hydrogen monoiodide is? Can you draw that structure? You may want to pause a second and do that. All right, hopefully you came up with HI. There's that molecule. It's a linear molecule. So the next thing we need to think about to figure out the intermolecular force is this a polar molecule or a nonpolar molecule? So I've got to go to my table of electronegativity. Because we're looking to see, will these molecules stick together? Is there an intermolecular force here? And so it is polar because our electronegativity difference is greater than 0.5. Again, the electronegativity of hydrogen, 2.1. The electronegativity of hydrogen, 2.66. So it's just barely greater than 0.5. And because it's a polar molecule, whoops, I thought I had one more thing on there. Because it's a polar molecule, the force here that would cause them to stick together is dipole-dipole, because HI is a dipole, there's two poles. The other HI is a dipole, so there's two poles. So we call this force dipole-dipole, causing those to stick together. Again, dipole-dipole forces occur in your polar molecules. Now, these dipoles, it's not like +1 and -1 like we have an ionic bond. It's much weaker than the ion-ion forces. All right, the next intermolecular force you need to know is hydrogen bonding. Now, hydrogen bonding is just an extra strong dipole-dipole force. And it exists only when hydrogen is bonded to FO or N. So how I remember this is I think of ET, phone home. Anytime H is bonded to FO or N, phone home, that's when we have a hydrogen bond. Where do we see this? In your DNA. So actually, these black dashed lines here holding the DNA together are those hydrogen bonds. This is also what holds water molecules together. Now, could we also say that those London dispersion forces are present and dipole-dipole forces are present? Yes, absolutely. But the strongest force is the hydrogen bond. And the hydrogen bonding is a very strong force. When they first discovered it, they actually thought it was a separate type of bond. Come to find out it's not, but the name stuck. Again, these are not real chemical bonds. Anytime that H is bonded to F, O, or N, and the H actually has to be directly bonded to those other atoms. So that's where you have to be able to draw the structure or look at the structure of the molecule. And there you can see a molecule of DNA. You can see that the H is directly bonded to the end, and that's why, to the N, excuse me, that's why we have hydrogen bonding there. Okay. Let's do a quick review. What type of force is this one? HBr, obviously polar molecules, two of them. So this would be dipole-dipole force. That's the strongest force that's here. Now, of course, London forces will also be present. Okay, what type of force here? Or perhaps I should say, what's the strongest force here? If you said ion-ion forces, you're exactly right. Now, can we have an ion with a dipole? Yes, we can. Then we would have ion-dipole forces. Just so you know, in these ion-ion forces, the greater the charge, the closer the distance, the stronger the attraction. So if we wanted to compare all of these forces, covalent bonds are intramolecular force is the strongest. And then our weakest force is our London or our dispersion forces. And remember, the size is the most important thing there. And so when you're looking at the periodic table, you should know the sizes of those atoms, because you're going to have to think about that when you're doing those London dispersion forces. So there can be a mixture of these various forces. We usually start with the weakest force and list all the way up to the strongest force. So let's take a look at this one. What type of force is this one? Now, of course, London dispersion forces are going to be present as well, because they're always present. But here I see I've got an ion and a dipole. And so this is going to be an ion-dipole force. That's going to cause those materials to stick together. What about this? What type of force would this be? So we've got a nonpolar molecule. That's why we have no charge separation. And then we have an ion. Well, that's going to be an ion-induced dipole force, or an ion in London dispersion force. Because what's going to happen is the electrons in this molecule, it's not a very large molecule, the electrons are going to move over towards that positive ion, causing a charge separation there. And so that's why we're going to have that temporary attraction there. Here we have a dipole doing the same thing. This dipole on the right is causing a charge separation in that nonpolar molecule. So we have a dipole, induced dipole force. Here may be another place to pause the video. Take a look at these. So hopefully you've paused the video and you're ready to identify these from the strongest intermolecular force present to the weakest. So obviously, in order to do that, you first have to figure out which intermolecular force is present in each. So let's take a look. Did you get them? So hopefully you found CF4. It's a nonpolar molecule. The only force that can be present is your London dispersion. In NH3, if you drew that out, you know that the N is directly bonded to the H. So anytime H is bonded to FO or N, it's a hydrogen bond. Neon, just an atom. So that would have to be London dispersion. PBr3, again, if you drew that out and you looked at your electronegativity difference between P and Br, you should have realized that that is a polar molecule. So if we put those in order from strongest to weakest, our strongest would be the hydrogen bond, and our weakest would be the neon, because it's both neon and CF4 are London dispersion, but neon is the smaller chemical species. And so once again, kind of looking at that electronegativity difference, to give you an idea of what's going on there. So this is our quick video review to get started with Unit 3. We've looked at, we didn't get into phase changes yet today, except for to talk about how we can turn any material from a solid to a liquid to a gas, but we did look a lot at intermolecular forces and a little bit at the properties of solids and liquids. I will see you this week for our regular class on Monday.